All right, we're ready to continue the normal approximation to the binomial distribution. Aren't those fancy words? This is example number 2. Building off of example number 1, again, I encourage you to watch these in sequence. So in example number 1, Mario, the basketball player, shot 5 shots. Now what? He's going to shoot 100 shots. All right? And the question goes on to talk about what's the probability he will hit at least 83 shots. So here's the deal. If you give a person 100 attempts at a task, like shooting a basketball, couldn't they have anywhere from 0 to 100 successes? In this case, hitting the shot, because he talks about hitting a certain number of shots. That's the probability, that's considered success. At least 83 shots. So we have all the numbers from 0 to 100. All right, Mr. Soybean didn't list them all. 0, 1, 2, 3, 80, 81, 100. At least 83 shots would be from 83 to 100, wouldn't it? So I want you to compare this to example number 1. What we could do is we could set up the probabilities for all the numbers from 83 to 100 and add them up. And that would indeed work, and that would give us an exact answer. So if you want to do it that way, be my guest. You got time to do it, I suppose, but that would be a very inefficient way to go after it. So let's talk about a different mathematical theory that might be useful to us. But first of all, we want to set up the fact that this is the probability that the number of hits is greater than or equal to 83, right? That means at least 83. And that would be the numbers from 83 to 100. Do it the old way if you want. Do it the assignment 15 way. Again, set up the formula for every one of those and add them up. But let's talk about this in a different way. So, we could, if we wanted, go and find those probabilities for every number from 0 to 100 and graph them. All right? Now, one of the things that I failed to do on assignment or example number 1 was to show you this. When he only shot 5 shots, that was no big deal to set up the formula for all those numbers from 0 to 5 and figure them out. And if you made a graph of that, when he only shot 5 shots, the graph of that, the bar graph, the histogram, looks something like that. Okay? So, okay, whatever. No particular pattern, just kind of jig-jaggy. Doesn't really resemble anything we've seen as far as a pattern. So just keep that in mind, that's when he shot 5 shots. Now, suppose we come to when he shoots 100 shots, and you could make this probability distribution for every number from 0 to 100 using that formula approach. I say partial here because there wasn't enough room to put all the values of x from 0 to 100. So let's say we had the numbers from 70 to 90 over here in this list of values, the number of hits, right? Let's talk about the probabilities from 70 to 90. And these numbers were all obtained using that formula approach that we talked about on assignment 15 and example 1, all right? So for example, the probability he'll hit 80 shots, if you do that formula, is about 0.0993, and so on. Well, if you make a graph of that, a bar graph, a histogram, this is what it looks like. Oh my gosh! So hopefully everybody would look at that picture and go, that kind of has a pattern that looks familiar to me, doesn't it? That looks like our good old friend the bell curve, doesn't it? Now it's not a curve, it's a series of bars, but it seems to resemble that pattern, okay? So here's the theory behind this new idea. The bell curve is called the normal distribution, and this is a binomial question. That's why this is called normal approximation to the binomial distribution. We're using a bell curve as an approximation, as a substitute for this particular binomial question. So, let's move to the notes that were uploaded to you and talk about when can you use a bell curve, a normal approximation to a binomial. Well, apparently, you can't always do it. When Mario shot 100 shots, it seemed to look like a bell curve, didn't it? All right. But when he only shot 5 shots, that don't look like no bell curve, does it? Okay? That don't look like no bell curve. So there must be some criteria that need to be met in order for us to use a bell curve as a substitute for the binomial. And here are the rules that very, very smart math people figured out. We can use a normal approximation to a bell curve. We can use, or normal approximation to a binomial, a bell curve as a substitute for a binomial experiment under the following rules. If the n times p is greater than or equal to 5, and both of these have to be true, and nq greater than or equal to 5, then the mathematicians of the world say, yeah, it's okay to use a bell curve as a substitute. So here's what I'm going to do here. If I'm looking at this question and going, you know, I could do the old formula approach and figure that out for all these numbers and add them together. Party at my house, woohoo! Wait a minute. Is it possible to use a bell curve as a substitute? And so here's my little picture. Bell curve, question mark? Can I use a bell curve as a substitute for this? Let's check these two rules here. So for this question, n times p would equal 100 times 0.8, which is 80, which is definitely more than 5. So you go, all right, so far so good, check. That satisfied the first rule. Now when you put and between two things, that means they both have to be true. So what I do is I check the first one, and if it fails, I don't go on and do the other one, but it worked. So then I go on and go, okay, so far so good. Let me try NQ, and that would be 100 times 0.2, and that's 20, and that's also more than 5. Now, there's a faster way. You could just pick the smaller of the P and the Q and do it, but let's just do them both. But the point is it okay to use a bell curve as a substitute in this question? Yes, it satisfied both rules. So we're about to change this question into a normal distribution type of question, and we'll move on from there, all right? So that's how you establish, without actually calculating all those probabilities and drawing a picture and saying, that looks like a bell curve. That's how you do this, is you check those rules, NP, NQ, 5, all right? So yes, it's okay to use a bell curve here. Now, that would be what it would work for on example 2. If I'd had more board space, I would have left example number 1 up here, but let's go back and talk about that very quickly. Let's go back to when he only shot 5 shots, all right? If you were asking the same question when Mario only shot 5 shots, you would hopefully say, oh, let me check those two rules, NP, NQ. The N obviously is a smaller number, it's only 5 now. So you go, and again, what I'm doing here is I'm checking to see, is it appropriate, according to the math nerds, to use a bell curve as a substitute when Mario only shot 5 shots, example number 1. NP is 5 times 0.8, which is 4, and you go, well, that's less than 5. Oh no. And when he only shot 5 shots, you go, nope, can't use a bell curve. And there's no point in checking the NQ, right? Because they both have to be true. So if one or the other fails, NP or NQ less than 5, no go. And I hope that would be exemplified by the histogram when he only shot 5 shots. That don't look like no bell curve, does it? All right? That don't look like no bell curve. You can't see my hillbilly teeth, so anyway, I guess we'll leave it at that. But I hope you understand, you got to check that rule, NP, NQ, and make sure it's at least 5 before you go on and attack the question as a bell curve. All right, but when Mario shot 100 shots, we're good to go. All right, so what else? Well, when we do bell curve questions, don't we need to establish the number that's in the middle? That's the mean. So we need to find the mean and the standard deviation. Back on assignment 15, when we did binomial distributions, we established the formulas for mean and standard deviation as being NP and square root of NPQ. All right? So if you apply that to this particular situation, again, I'll get this out of the way. We already checked to make sure it's okay to use a bell curve. And it is when Mario shoots 100 shots. So the mean, NP, would equal 100 times 0.8, which which is 80, all right? And 80, oh, so 80 goes in the middle here, doesn't it? Now look, wouldn't hitting 80 shots be the highest probability? And so I'll take you back to that histogram that I had built. 80 shots had the highest probability using that formula approach, all right? So that's why I made that graph go from 70 to 90, because that's where the majority of the, the picture would exist. So I hope you now see 70 to 90, mean 80, all right? Standard deviation, square root of NPQ, square root of 100 times 0.8 times 0.2. I should be able to do all that math in my head. That would be 80 times 0.2, which I think is 16, and then the square root of 16. But I'm going to double check this, because if I mess up this number, it's really going to jack things up. Yeah, that's the square root of 16. And so the standard deviation is a nice round 4. That's fortunate. It won't always be. When we go to example number 3, we'll have a crazy standard deviation, but a messimal. But that's okay. Let's take advantage of that. Okay, so far so good. We've got our bell curve. Now, I would say that step 3 here, when you do this process, is the most important. It's the easiest to forget, and it's the easiest to do incorrectly. So I just want to tell you on example 2 here, I'm going to talk through quickly how you do what they call correct for continuity by 0.5, bold, correct for continuity by 0.5. The mathematicians of the world have discovered that if you're going to take a discrete binomial question and replace it with a continuous normal, you have to do this adjustment called correcting for continuity. And I want you to understand, we're superimposing a continuous curve over this discrete binomial question. And so again, the mathematicians of the world have discovered that you have to make this little adjustment we're about to make this approximation just a little bit better. So, on example 3, we will spend a bunch of time practicing how to correct for continuity by 0.5. If the first one doesn't make sense, hang with me and go watch example 3, and we'll continue to get better and better at it, all right? But here's what I do. Underneath this original question, I draw a number line representing x, and a picture of greater than or equal to 83 would be, here's 83 with a solid dot on it, right? Equal, and then greater. All right. Now, usually I'm able to ask you guys what you think, and it's going to be hard for me to hear you. Plus, you're all maybe looking at this at different times of the day. But when we correct for continuity by 0.5, we're either going to add 0.5 to the 83, or we're going to subtract 0.5 from it. Those are our choices. Do we go up by 0.5, or do we come down by 0.5? And to me, and we will keep practicing this, so hang with me, example 3, we'll talk and talk and talk. I wrote down, on example 3, I made every scenario I could think of so that we could go through them, all right? So I will again tell you, if this one doesn't make sense, hang with me and watch through all the examples of example 3, and it'll hopefully clarify, all right? So, here's what I'm looking at. Do we want to include the 83? Yes, equal to. It said at least 83, which means linguistically include 83. So my thought would be, if we go up to 83.5, and on up, we would lose the 83. We'd be above it, and we'd be running away from it, and we would lose the 83. And we don't want to do that. We want to keep it in the discussion because of that equal to. So the proper way to do it, and again, we'll keep practicing. Example 3, all right? This is the key step in this, is correcting for continuity in the proper way. Remembering to do it and doing it in the proper way. But in this question, we need to come down to 82.5. See, 83 minus 0.5, 82.5. We need to come down to 82.5 and run through the 83 and keep 83 in the question because of that equal to, because of the words at least. So, here's the critical step here. We will adjust that number to 82.5. we're going to come down by 0.5 from the 83. There you go. The rest of the question now should be familiar to us. We have a variable called x. We've got our bell curve as established earlier. We have the fact that the mean is 80. All right, so we put that 82.5 on the picture. And greater than or equal to 82.5 would be this area here. All right, and the rest of the question, frankly, should be stuff that we've done before. So I guess I'll practice it with you, but solve it as a normal distribution type of question. So the hope would be now everybody's looking at this going, oh, that is so assignment 17. I have a normally distributed variable. I know the mean and the standard deviation. Cool. So you would hopefully flash back to assignment 17, right? Whoa, man. All right? And you hopefully remember that back on assignment 17, when we had what was called a general normal, so I'm going to click you back to those notes, all right? Back on assignment 17, when we talked about normal distributions, z, oh yeah, we have to make everything z, don't we? All right? So the point was, when we had a general normal variable called x, the key was to change it into z by standardizing. Standardize! And so here we go again. We're going to translate that x into a z and finish the question like we did on assignment 17. So you'll notice that I drew a standard normal bell curve with 0 in the middle, shaded the upper tail much like that picture, and then it would be a matter of changing that x into a z. I hope everybody's going, oh, this is so assignment 17. Oh yeah. All right, and then you standardize that score, right here. Z equals x 82.5 minus mu 80 over sigma 4. That's why we needed that mean and standard deviation that we established way back when. All right, and so that z-score becomes 2.5 divided by 4, which is 0.625. And I want to remind you that we, because of the limitations of our table, need to round those z-scores to 2 decimal places. So 0.625 becomes 0.63. Notice that's positive because this was above the mean. All that we've talked about before. All right, it keeps building, it keeps building, it keeps building. And then you would hopefully go, hey, look at that. I got a standard normal now. So you jump up here to this, standard normal, after you standardize it. And now you're like, well, this is just assignment 16, isn't it? And then you would hopefully say, well, now I can just go and consult that beautiful table, bell curve, right, to find that area. So here you go. And I know you guys have been missing this, so. Table time. All right, and so we look up the 0.63, right? And that 0.63, all right? Oh, this is so assignment 16. And that's 0.2357, 0.2357. And remember, this table always gives you that middle sliver there, doesn't it? Table always gives middle sliver, all right? Sorry, too many props over here. Where did the man go? I don't know. I'm sorry for wasting your time. Look at that. Table always give middle sliver, right? But look at the picture. This is assignment 16. If we want this upper tail, wouldn't we need to take the upper half of the bell curve, which is 0.5, and subtract that middle sliver to get the region we actually want? So here we go. Space is at a premium. Let's do that math up here. So 0.5 minus 0.2357. Oh boy, I'm nervous. Let's see. That would be what? 0.2643, I think. All right, there's our answer. 0.2643 would be that approximation here. I want to remind you one more time, this is called an approximation because to get the exact answer, a person would need to apply that binomial formula to every number from 83 to 100 and add them up. That would be exact. That would be the bars on the histogram. Exact. We superimposed a bell curve over it when we did it this way, and we're off a little bit, all right? So the point is we're sacrificing just a little bit of accuracy, exactness, for efficiency, speed, all right? So that's the idea behind that. So that is example 2, and we will now transition to example 3, where we'll practice the different ways that we correct for continuity. Sounds like a plan? All right, see you in a few. Hang in there, everyone. We can do this. Yes!